SRF team to conduct dark field, hence why we are here. So the study we worked on was quantifying microscale drivers, fatigue failure with X-ray characterization, as well as crystal plasticity simulations. So I'll start off with some motivation. Structural materials in the engineering universe undergo fatigue loading, and will eventually start to form fatigue cracks and eventually fail. One of the places where this can occur is at grain boundaries, and particular to the materials that we're looking at today, nickel-based superalloys, they tend to form at twin boundaries, to be specific. In the top right, we have an image of an HEDM reconstruction showing a fatigue crack growing out of an inclusion between two different grains. So we know that grain boundaries are general or hotspots to be able to initiate cracks. So we'll be telling a bit of a story today with a multi-scale characterization. And the goals of this characterization was to take the physical behavior at the specimen scale that we see to the underlying physics at the micro and the nanometer scale with dark field. And from this, we will try to identify stress concentrations and gradients at these grain boundaries to help understand the phenomenon of crack initiation. To achieve this, we used three different tools. The first was HEDM, also known as 3D XRD, where it determines the grain average strains and orientations, as we know. And then moving on to dark field, we're able to zoom in on some feature of interest. And then finally, we want to compare dark field to something to evaluate the validity of the values that we're seeing there. And so we brought in a crystal plasticity simulation. So a quick overview of all of the places that this specimen has been. The material that we worked with was LSHR, low solvus, high refractory. It is a nickel-based superalloy, as I said. And if you're unfamiliar with these, they're typical jet engine disc alloys. They're very good with high temperatures, maintaining their strength under high temperature applications. So we began conducting near-field HEDM, which I'll show a little bit later, but it's able to reconstruct microstructures, as you can see here. Then we proceeded to conduct fatigue loading coupled with far-field HEDM. And here we can calculate we can reconstruct the grain average strains and thus the stresses at different load states as we're cycling this material. We cycle for 1,000 cycles to 1% macroscopic strain with an R ratio of 0 and displacement control. After we did this, we then wanted to choose a grain of interest for extraction. We needed to extract a sample to be able to bring to ESRF for further characterization. And once we did that, we used dark field to really study the intragranular misorientation and strain around some feature of interest in this grain. And then finally, as I said, we brought in a crystal plasticity model to compare to dark field. So I'm sure we're all familiar with HEDM, specifically near field, but for those who are not, it's a rotating diffraction experiment where we place a detector rather close to the specimen on the order of about a few millimeters, about 10 millimeters, and it provides really high spatial resolution, and you can reconstruct microstructures as you can see here. Our microstructure in particular, fairly equiaxed grains, random texture. I have an IPF plot later in the slides, and the average grain size was a little bit under 100 microns. We then conducted this fatigue testing coupled with far field. And here we really wanted to see how their strains evolved as we cycled the material. So you can see our loading curve in the middle. That was for the first cycle. You can see the red points illustrating all the different far field scans that we took. Afterwards, we took scans at 10, 100, 1,000 cycles to be able to see how those stresses evolve within the material. So far field, we place the detector further away. We get much higher angular resolution, similar to what you can see in dark field. And from that, we can get grain average statistics. And if you have the correct material properties, the stiffness components, you can bring elastic strain and you can convert it to stress. And so on the right, we have two different pictures. Both are the near field reconstruction that you saw previously, but instead of the IPF colors, we've colored it with the stresses reconstructed from far field. And so what you can see is that heterogeneous distribution of stresses within our microstructure in the unloaded state. And then we load at a loaded state after 1,000 cycles, we still see that heterogeneous distribution, and even a larger distribution where we're seeing, instead of just a 300 MPa spread, we have something more similar to a 500 or 600 MPa spread across all of those grains. So we start to see this evolution, and now we want to choose a grain to zoom in on and extract from our larger sample to then proceed to do dark field at. All of this up until now, all of the X-ray characterization was done at CHESS, the Cornell high energy synchrotron source in New York, specifically beamline F2. So we wanted to bring this to ESRF for dark field. One of the major restrictions we had was, since this is nickel, we had to extract a much smaller specimen to be able to have enough flux at the beam to see anything on the detector. So we needed to extract a grain of interest, which required us to first find a grain of interest to look at. And we had a few requirements that we needed to meet. The first one was defined by the setup for dark field, that we only have a limited range to tilt the motors. So we needed to have the lattice planes that we were going to look at well aligned with the extraction axis. So we found a few candidate grains for that. And then we also wanted it to be close to the surface to allow for easy extraction in the first place. So we found some candidate grains there. And then finally, we wanted to make sure that we had enough plastic deformation induced within our grains of interest for actual characterization. To do that, we looked at our far field data a little bit more closely. Specifically, we looked at the diffraction spots themselves and how they evolved with loading. So you can see at the bottom, I have a initial and then a deformed diffraction spot of the same grain. It's the same spot just after some sort of fatigue loading. And what you can see is that it's now changed. And in particular, we're looking at two different metrics here. We're looking at azimuthal spreading and radial spreading. The azimuthal spreading shows us information about the lattice curvature that's contained within that single grain, whereas the radial spreading tells us about what the heterogeneous spread of elastic strains are within that grain. And so that's what we're looking at there. We wanted to find a grain that had clearly spread after fatigue loading. And so we found a few candidate grains there. So once we chose our grains, we now needed to find them and to allow for surface access. The grain of interest that we're going to be following today was subsurface, so we couldn't see it directly on an EBSD map, but we were able to find the location. So we conducted EBSD on the surface, and we compared it to our near field reconstruction. And with that, we were able to get that spatial match. You will note as a side that we did have a decent match between the near field and the EBSD. Many of the grains, you can see there with corresponding grains in both of the two reconstructions. The near field is, of course, a little bit subsurface. Near field doesn't have the best resolution at the sample boundaries themselves, whereas EBSD is right at the surface, but yet we still do see a good match. So now we know where to find the grain. Now we just have to extract it. And that was quite indeed a process. It required a lot of focused ion milling, focused ion beam milling. It first began at our collaborators at AFRL, where they marked each individual place for extraction. And then they shipped it to our collaborators at NASA. And they have a plasma fib where they took out very large amounts of material around each of these extraction points. Some of those holes that you're seeing there are about 250 to 300 microns deep, so quite a bit of material was removed. And then it was shipped back to AFRL for final extraction, where we now can mount these small samples, these small specimens, on top of a brass pedestal which has a nice birthday cake sort of structure so that we wouldn't have interference from that during scanning at the SRF. So then we brought this sample across the pond for further characterization. The first thing that we did was we used diffraction contrast tomography, which I think we'll probably see a little bit later. We'll see more about that in further talks. But it's similar to near field where we have a close detector and we're able to have high spatial resolution. So we reconstructed our specimen that we now extracted from our larger sample. We found that we did indeed cut out the grain of interest, or at least part of it, and that's that green grain, that large green grain that you see there. And then we also further learned that we have a coherent twin, and that's what you can see here, this magenta twin in the background. And that's what we're going to be looking at in the future. So keep in mind that that is there, and we found that with DCT. From now on, all of the X-ray characterization that you can see was, of course, done at ESRF ID06. So we've seen this a few times now, of course. I won't spend too much time on it, but I did want to show, for those who are not necessarily familiar with what we're actually seeing as we scan during dark field scan experiments, is that we can really see this grain coming in and out of the diffraction condition. In particular, the GIF that you're seeing here is a movement of the objective. So what we're going through there is we're seeing different parts of the grain with different values of elastic strain or D-spacing. A few parameters that we had, we used a 1 micron condensed beam. Our magnification was about 15 times, and those were our step sizes for alpha and beta. I have named the two orthogonal tilts alpha and beta rather than eta and chi or other variable names, just for simplicity in the following slides. So here you see a GIF of moving the objective lens, but what if we wanted to then see what they look like when we move through alpha and beta? So this is for a single slice of the grain of interest. And what you can see here is a clear orientation difference between different parts of the grain. And this is how it appears when on the detector itself. So we see in the middle, the center of that grain, we have one orientation followed by here at the grain boundaries, we have a different orientation. And similarly with beta, we're able to see from one side of the grain to the other a big change in orientation as we're scanning through. And this is what we were looking for. And then we've seen this in varying color schemes, but here I have the spreads in alpha and beta, and you can indeed see, as we saw in the GIFs earlier, where the interior of the grain in alpha holds one orientation relative to the exterior, the boundaries, and then beta we see that side-to-side difference in orientation. We can combine this, of course, into these beautiful mosaicity plots, which combines the two. And then I've also put it into a misorientation, so to speak, where it's the sum of squares. But here it just gives you the magnitude of orientation difference. So we do lose out on some information, and that's something to keep in mind in the future slides. Whereas we don't capture these two being the different orientations, yet we do just see that they're the same, roughly the same magnitude away from that arbitrary 0 that we chose. So up until now, I've shown only these images here are just of a mosaicity scan. We also conducted mosaicity scans coupled with elastic strain. So we sampled the whole three-dimensional search space that we have available with dark field. And one of those reconstructions is shown here, where we have similar misorientation and mosaicity plots, as I showed you before, but we can also have elastic strain that you see there on the left, where we see different amounts of elastic strain and as we move through our grain. One of the biggest challenges of this experiment was linking all of our different length scales. So we started with that larger sample, which was about 1 millimeter square, and then we extracted this small pillar, which was only about 200 microns by 100 microns in diameter. And then we further only sampled one specific grain within this microstructure, but we did multiple scans. So we're able to stack those dark field layers, as you see here, into something resembling the grain of interest itself. And then we're able to spatially link those dark field layers with the DCT reconstruction. And that's what we've done here. With this linkage, we'll move in the future, we'll be able to link DCT with near field reconstructions that we did prior, and therefore we can link all the way from the smallest length scale with dark field all the way up to the largest length scale that we looked at with near field. So I wanted to bring us back to looking at this coherent twin relative to the one dark field layer that we're going to be studying for the rest of these slides. That one layer, that is a coupled or combined mosaicity and elastic strain scan. So we had all the information available. And note that it's located directly below this coherent twin. So just keep that in mind in the future. So the goal now is we wanted to determine what the effect this twin boundary itself had on the dark field layer that you can see there. So in order to do this, in order to find this effect, we brought in the help of a crystal plasticity model. And for those unfamiliar with it, effectively we give a model of voxelated crystal orientation data, which is from near field, as well as the material properties that we know, such as the hardening parameters and the stiffness tensor parameters. And then the model is we macroscopically strain the model, similar to how we did at CHESS. And then with our constitutive relations and knowledge of the material deformation, as we see here with the plastic flow rule, we can then get a voxelated form of the stress and strain tensor. So for every single crystal orientation, every voxel from we give this model from near field, we're able to output the stresses and strains. And now with that voxelated data, we can start to compare it to the dark field images that we saw prior. One last spatial linkage was necessary, and that was linking the DCT volume to the near field volume. And so that's what you see here. The near field slices are in the background, whereas the DCT volume is in 3 dimensions. And you can see that we're able to nicely match up the 2 microstructures. We of course didn't expect a perfect match because we were looking at 2 different specimen sizes, but the grain boundaries lined up very well indeed. And now that we have spatially linked all of the length scales from dark field to DCT to near field, where the model is at, now we're able to move forward. So a quick result from the model itself, we gave it that near field data, and now we've outputted that voxelated stress and strain data. And what you're seeing here is just the effective plastic strain, where we start to see nice strain accumulations of plastic strain along grain boundaries and other microstructural features. For reference, our grain of interest is below this point roughly, but we'll be looking at individual slices of that grain of interest in the following slides. One thing to note here is our goal, of course, is to determine the role of that coherent twin. And in order to do that, we instantiated our crystal plasticity model twice, one with the twin and one without the twin. And so one, instead of with the twin, we have reconstructed near field with the twin presence. And then the second one, we have removed that twin and instead replaced it with the parent grain. And so that's what we can see in this slide here. We have our crystal plasticity model of our grain of interest in the background, overlaid with the dark field image in the foreground. So you can see that they're on top of each other here. And then here, without the twin and with the twin, this is the elastic strain on the 220 planes. And they're all on the same scale bar, which was a nice match to see. That happened naturally without any movement of the arbitrary zero. We were able to see that the elastic strains were the same. And then here, of course, for your reference, is the location of the coherent twin relative to the crystal plasticity slice itself. So these, now that we have that spatial matching, we're able to link everything together. And the big takeaway here is that when we had the twin instantiated, we're able to see the effects here. So we have a high strain concentration here, a high strain directly next to a lower strain value here. And that's what we can see in this part right here from the dark field. So we see a good match, both in value and spatial locations of our elastic strains. And as a side note, we did see that if you were to take a line from here, from the high region of elastic strain to the low region, and then convert that strain difference to stress, we're seeing about a 400 MPa jump in stress with just a change of 30 microns within the grain of interest. So here we're really starting to see those large strain and stress gradients directly in the area below a twin boundary in this parent grain. And to bring us back to our motivation, twin boundaries are known for locations of fatigue failure, and this is just one indication of the response that the parent grain has with a coherent twin on the stress gradients. So now we want to look at the plastic strain and misorientation. We're comparing here equivalent plastic strain to the misorientation found with dark field. Here we're looking for just a qualitative investigation. And so what do we see when we instantiate the twin in our crystal plasticity model? Well, we start to see a lower value of plastic strain here, followed by a higher value of plastic strain on the side here. And we don't see as strong of a gradient when we don't have the twin instantiated. And we see a similar effect in dark field, where we have a large gradient of misorientation from here to that area there. And so we're seeing a good match again in the plastic strain and misorientation comparison. One final note, we wanted to look a little bit deeper, so we extracted the information just from a single voxel in this region that we're seeing that large gradient, and we found something interesting. What I've plotted here is alpha and beta, the two orthogonal tilts, as a function of elastic strain. And you can see that we very clearly have a bimodal distribution of intensities here. So this is telling us that there's just two orientations at two separate strain values within this single voxel from our dark field investigation. Just as a note, that's about 0.2 degree orientation difference. And the elastic strain difference that we're seeing here in the alpha plot corresponds to about 300 MPa. So within a single voxel, we're seeing about a 300 MPa strain or stress difference. Possible explanations here, we could have a decoherent gamma prime precipitant phase where the gamma prime is holding a different stress value than the gamma matrix. Otherwise, we could have a very high dislocation content where we have this nice cell structure from fatigue loading, where the interior of the cells hold a different stress and orientation value than the cell walls. So I'll close up. I believe I'm a little bit early. I think I spoke a little too quickly. Sorry for that. But we provided a framework for this multi-scale characterization, and we showed the ability to move through different length scales, to zoom in, to start at a larger volume of about 1 millimeter squared, to zoom in all the way down to the level of dark field and investigate features directly under our coherent twin, And we started to see these nice gradients of intragranular misorientation and strain. We observed this twin boundary with DCT, and we observed the elastic strain and misorientation gradients with dark field. We then brought in the crystal plasticity model to show us that indeed these gradients are caused directly from the existence of this coherent twin in the microstructure. We also saw, if we evaluated the value of these stress gradients, the difference of about 400 MPa over 30 microns. Again, this region is known for fatigue crack initiation, so this was an interesting find. And this just shows the importance of considering these stress and strain gradients in models. My acknowledgements. We had quite a few people who helped out on this project. A lot of the fibbing was done at NASA, the plasma fibbing, as well as the collaborators at AFRL. The nice birthday cake shaped pedestals were manufactured by Basil Blank. He did a great job there. EBSD analysis was done by John Rotella. The synchrotron sources, both CHESS and ESRF, Beamline F2 and IDO6 respectively. We had help from Dr. Peter Koh and Mustafa John Kutsal individually, and they all, as well as all of the collaborators at both synchrotron sources who made this possible, and our funding sources, of course. And with that, I will wrap up and I'll take any questions. Thank you.
Thank you very much, Sven. It was a very nice talk. Let's see if we have questions. I see some people. Yeah, Yubin, go ahead, please.
Okay, thank you very much, Sven. That's a very nice work and a lot of interesting stuff. I had a question regarding your early slide about the residual stress in the starting condition before you load it.
Oh, I see.
This is a pure nickel, right? I was wondering what
This
could be
is-
the reason.
This is a nickel superalloy.
Okay, nickel superalloy, but still it's okay. Do you have mind to give a little comment about how this residual stress could build? Because even superalloy, there should be similar expansion coefficient around different directions should be the same, I guess.
So we definitely, this is typical for what we've seen in many of the superalloys that we've looked at with HEDM. This could definitely come from the manufacturing process and having residual stresses left over after annealing. And that's
Okay.
where I would expect the majority of this would come from.
Yeah, and the measurement is from the far field measurement, not the near field, I guess.
Correct.
Yes,
This is
you
from
can.
far field. Yeah.
Thank you.
Henning, please go ahead.
Well, first of all, this is really intriguing. I mean, this multi-scale characterization is certainly one of the things that we are hoping to do also in the future. So my question relates to, to combine this multi-scale type of characterization with your crystal plasticity model. I mean, where would, if on your wish list, what would you want? I mean, what is most important here in order to progress? Is it to have a larger volume inspected? Is it to have higher spatial resolution? Is it more strain components? What is it that we need to do to improve even further?
I think one of the most interesting things moving forward, since we're able to, with far field, see so many different grains, if in dark field we could start to look at adjacent grains and the interactions between them, I think that would be a big step forward. And I think that would require careful characterization with 3D XRD or far field HEDM prior to locate two grains that are next to each other that have lattice planes that are well aligned that we can bring to ESRF. And I think that would be a big step forward, or at least a good progression from this work.
Thank you.
Maybe a little comment on that. Actually, I had a question related to that. Do you have this this coherent twin next to your main grain? And you can see in the near field data that there's quite a bit of orientation difference. But given that the sample has only a few grains and you know all the orientations, I wonder if you still have the sample, and I wonder if you have any plans to check the other grain and see if similar strain developments and orientation changes around the twin boundary is visible there as well.
The sample, we do still have this. I believe Wolfgang Ludwig actually has the sample with him. So it might still be over at ESRF, but indeed the sample is still viable for further investigation. One of the points against it, however, is that it's nickel, so it takes quite a bit of beam to punch through, and the scanning time took a long time for these scans.
Yeah. For the another remark, I think this experiment was one of the first ones that we used the polymer lenses at 33 keV in a user experiment, a friendly user experiment. I see Ashley has a question. Ashley, please go ahead.
Yeah, I was going to change the topic though, if you wanted to finish.
No, I think I'm good, unless Sven wants to say something else.
Okay. You have more beam now too, so.
Yeah.
Can you show the video on the left of, I think it was slide 12? Yeah, the alpha. It looks, at first I thought this was tomography, but it's not, right? It's just tilting. But at the center of the grain, it looks like you have intensity at the beginning of the tilt and at the end. So it's almost like you have this bimodal orientation all over the grain. Does that make sense? Like if you did a center of mass mosaicity calculation, it would just become the average of those two extremes. But when you actually watch this video, it looks like you have a lot of intensity at the start of the rocking curve and a lot at the end. So the whole thing is bimodal, and if you did just the average calculation, that would sort of get washed out. But you know, if you have these precipitates all over the sample, then that would be one explanation for it. But I was just wondering if you saw that and thought about it.
No, I didn't see that directly when looking at this scan, though I know when I probed individual voxels to look for a similar type of bimodal distribution, it wasn't nearly as distinct, and I don't believe I saw it as a actual bimodal distribution. Most of them just looked like a wider curve, a wider distribution.
Okay, thanks. I just thought it was kind of neat looking, and how do you think through that? So, okay, thanks. Nice work, by the way.
Thank you.
Do we have any other